Hello everyone, my name is Zheng Chang. You can call me Zhang. I'm currently a master student at University of Calgary. So the purpose of this video is try to share my knowledge about the isotope doping methods. And if you have any questions, you can contact our group leader, Dr. Ben Tutelo. And if you have some detailed questions about this slide, you can also contact me, but my email address will be cancelled off when I was graduated. So the first question is, what is isotope doping method? So when I was learning this method, the following papers really helped me a lot. So these three papers are really great papers describing this method. And the last one is the paper wrote by me and my supervisor, Ben Tutelo. It's currently under review. You can Google it to see any details of it. So what is the isotope doping method? So if we imagine we have an experiment going on, the solid in our solution is talc, which is a natural mineral, and the formula of the talc is Mg3Si4O10OH2, and the fraction of the silicate in talc is natural composition. So the silicate composition fraction of 28 should be 0.9223. The fractionation of 29 should be 0.0468, and the 30 should be 0.0309. And if we doped the solution with almost 100% of the 29, so let's say the 29 is almost 100%. So we can, if there is any interactions between the mineral and the solution, which can be reflected by the isotope composition of the solution. So let's take this as an example, which is also the talc mineral in it. So the 28 should be, fraction should be 9223, and the 29 should be 100%. So if we imagine we have the solution and we have the minerals, we have the reactors. So at the time 0, the silicate concentration can be separated as 28 and 29. So at the time 0, if we say the 29 is 2 micromole, and this is 0 micromole per liter, and so at the initial time it's almost 100%. It's 100% of the 28, right? So there are three situations we can think about. The first situation is if there is only dissolution happens. So after a time, if there is only dissolution, the 28 silicate in the solution should increase, right? And the 29 silicate should keep the same. So this is the first scenario. And the second is if there is only precipitation happens. After time, the 29 in the solution would decrease, right? And the 28 should keep the same, because there is no source of the 28, because there is no dissolution. And the third scenario would be if we have both the dissolution and precipitation. We can imagine after a time the solution would the 28 should be increase and the 29 should be decrease, right? So we can know that from these three conditions, the isotope tracer can separate the dissolution rates and the precipitation rates at the same time. So that's the use of the isotope doping method from my perspective. So the next video gonna be how to derive the rate equations to quantitatively describe the dissolution rates and the precipitation rates at the same time. So be free to watch the next video.